morning, everybody. Oh, well, that was weird. Okay. Sorry, I have a lot of too many things open here. Wow, my hair is just. I know I say this like every class, but every day I'm like, wow, my hair is really special. When you take 16C, we'll talk about surface. That's more of a 21C thing, really. So, but my hair is often a model for a surface in 21C that we talk about. It's kind of interesting. Anyway, not really the point of anything, but you know, sometimes we get distracted by our own selves. Let me give you guys the usual things. Here are the links to the attendance, of course. Please go fill it out like you have every class, as well as the link to the tutoring and a link to the end of the quarter evaluation. Please, if you have not filled the end of quarter eval out yet, do so. What else did I want to say before we get going today? Just a reminder that you do still have the option to change the class to pass, no pass, if that's something you're interested in doing. Oh, I forgot my water. I'll get that in a second. So you have until, I think, next Friday to change to pass, no pass if you want to, or change back from pass, no pass if you change to pass, no pass, but then feel like you're getting like a really good grade. Like, oh, I should get the grade. So you have until next Friday, I believe, to change. Do make sure that you talk to an advisor if you're concerned about your major requiring you to take the class for a grade. Also a reminder that, oh, actually, let me double check something really quick, because I was talking to Sarah this morning, and I know I've been saying that I think you guys should take 16C in summer session 1 if you're going to take 16C, but I actually don't know if it's offered summer session 1, so let me double check, because I would hate to be saying that you should take something in summer session 1 and it's not actually offered. So let's take a real quick look. I'm looking at the class search tool here. Course title. Sure, let's just go with that. Hopefully you guys are all doing well. I know we're getting very close to the end of the quarter here. So let's see, in the summer, is there a time cutoff for the pass? That's a good question, Nicole. I don't actually know the answer. I will try to figure that out. I would imagine if it's a day, it's probably like before midnight or something. But I will follow up on that, because I don't know the answer. But I will follow up and find out, and then I will post that in Canvas for all my Canvas classes. So cut off for pass, no pass. I'll find that out. Let's see here. So for I wanted summer session 1. Sorry, summer session 1, 2020. Probably not, but let me see if well, I'm looking right now. So let's take a look. Sorry, I accidentally searched fall though. What are you saying it is too, Martha?
Oh, it's just I'm enrolled in 16C for the summer session. So
there you go. Well, thanks. So yes, 16C is offered in summer session 1. It says currently that the instructor, his last name is Chu, or Shu, C-H-O-U. I'm not familiar with them. I imagine you could probably find them on the math department webpage, and also probably on Rate My Professor. Not that that's always a great source of information, but it's a somewhat useful source. So yes, it's offered in summer session 1. There's one section of it, I believe. Let me double check. Yeah, just one section. I imagine that the grad student, it usually is in summer session. I definitely taught my first class as a grad student at UC Davis in the summer. It was Math 16B. I did not do an excellent job. I'm sure I made it way harder than it needed to be. So just be aware, right? That taking it, not that, I mean, you could also take it during the regular quarter and have a regular, faculty member teach it. And it could also be way harder than it needs to be. So really either way, it could be anything. That said, I still think summer session 1 is probably a good time to take it, because you'll have more resources like myself and other people available, like Claire, we'll have office hours over the summer to help you guys out. So I would still recommend summer session 1. I think that's where you'll get the most aid from us. But certainly, I think it's also offered summer session 2. Let's take a quick look now that we're looking at things. Summer session 2, 2020. Let's see. Summer session 2. There is also Math 16C. It does not say who's teaching it yet, though. So that's all I really know. Let's see. I feel like there was something else I wanted to say. Oh, Nicole, I'm not sure if you saw, I put an answer to your discussion question. I think after the point you got to, you can just use the quadratic formula to solve that equation. So hopefully that works out. We can definitely do some examples of those kinds of things today if you guys would like.
I had a question about my answer. So how do I enter it into WebAssign if there's like two different answers?
Well, so only one of those answers should be correct. So actually, let me go back and look at the works. I've got it. Oh, I had it pulled up right here, and then of course it went away. So let's actually, this is not a bad problem for us all to look at. So let me grab it real quick here.
I can send you like the whole, or I can like.
It'll be faster if I just look at it.
Okay.
But thank you.
Because there was two parts to it. That's just the medium part of it.
Sure. One sec. So let's get everybody on board here. But yeah, it's a good question in general. So I think it's worth looking at. Oh, I forget where it was. I'm smart. Sorry. One sec. There we go. That'll be the best. So let's see. Let me make sure I've got this right, and then I will. Okay, so here is what, I don't know, let me try to light in here. Also, Sarah said to say she missed seeing you guys. She really enjoyed being your 16A teacher and misses you all, and said to say hi back. All right, so here's the question, or here's part of the question Nicole asked. And Nicole, if you want to clarify things in a minute, we can, but the part of the question that we were looking at, at least that I saw, was to find the median of the function, or the probability density function, f of x equal to 6/5 minus 2/5 x on the interval from, oh, I actually don't know what the interval is. Could you tell me what the interval is, Nicole?
0 to 1.
Okay. And is there other parts of the question you would like us to explore? Because I'm certainly happy to. I just don't know what they are.
It's just the other one is just finding the mean and median.
We can do both.
Thank you.
Of course. So both of the, so what should I say? Generally, the process for finding the mean or the median of a probability density function that's continuous is always the same. For the mean, it's always going to be the integral on your entire interval. So more generally, if it's right from A to B, it's going to be the integral from A to B of x times f of x dx. Right, just like the mean for a what's the word I'm looking for? For a discrete random variable, right, where you just have like the list of things with probabilities, you would do the sum or the sigma notation of x times f of x, or p of x is I think what they called it. So that's how you calculate the mean. And the median is a little bit, usually the median is a little bit wonkier. It's going to be the integral from either your lower or your upper limit. Either way is fine. From a to m of your function. And you're going to set that equal to 1/2 and solve for m. So for the median specifically, you're finding the place on the integral where the area to the left is equal to 1/2. Right? So if like, so for example, and this is A and this is B, and maybe my function looks something, I don't know, maybe it looks something like this. And we know that if it's a probability density function, the area under the curve has to equal 1, right? That's one of the requirements for being a probability density function. We're trying to find the spot where exactly half of the area is on the left and half of the area is on the right. So you could, usually most people I think default to doing the lower limit to m equal to 1/2, but you could also equivalently set the integral from m to b of f of x dx equal to 1/2 and solve for m. Either way works fine. So you should pick the one that seems like it has the easier limit of integration. in this problem, I would definitely do the integral from 0 to m, not the integral from m to 1, because it seems easier to use 0 than it is 1. Okay, so let's actually calculate things. And let's go ahead and do the mean first, because the mean's probably easier or more straightforward anyway. All kinds of pictures on here. And I don't know if this is more what Merck's is doing or what FAM is doing, but I know today is typically our FAM day, so after we do this problem, if there are students in FAM's class who have questions, please speak up and let me know. So to calculate the mean, we're going to do the integral from 0 to 1, because that's our interval in this case, of our function, of x times our function. And I don't remember what the function was, so we look back, it was 6/5 minus 2/5 x. Something to think about in each of these problems is that the mean should be between your limit of integration, right? The average of things between 0 and 1 should be between 0 and 1. Similarly, the median should also be somewhere in between the interval. You know what I do? So, no, that's not, sorry. So let's distribute the x. So we have the interval from 0 to 1 of 6/5 x minus 2/5 x squared. Integrate or anti-differentiate. I'm going to get 6/5 times x squared over 2 minus 2/5 times x cubed over 3 from 0 to 1. We can go ahead and plug in. So let's see. I'm going to get 6/5 times 1/2 and I plug in the 1. I can just write it out. Minus 2/5 times 1/3. And then I would plug in 0, but I'm going to get 0 for just things, right? I plug in 0 here, I get 0, 0.
Did you forget to add the 2 under the x squared?
I might, no, I don't think so.
Oh, never mind. You wrote it on the other side. Never mind.
Okay. So let's see. This is going to be a 5. So this is 6/10, which is 3/5. I guess I can reach the 3/5. And this is 2/5 times 1/3 is 2/15. So let's change this to 3/5. And then multiply it by 3 over 3 to get 9/15 minus 2/15, which is 7/15, which I assume is correct. It certainly is between 0 and 1, so I feel good about my answer, at least in that regard. It might be time for some more new pens. I'm all new pen happy here. So the median, I might want more space for median. So to calculate the median, we're going to do the integral from 0 to m, or 1, or m to 1, right? Either way would get the right answer if we do the right work, of just the function, the probability density function, 6/5 minus 2/5 x dx. And this is going to turn out to be a little bit funky, I think, at least, unless, yeah, no, just so I'm going to do, right, I'm going to do 6/5 x minus 2/5 x squared over 2, and I would definitely cancel the 2's there, from 0 to m. Yeah, 0 is definitely the right choice here, because when I'm plugging 0, everything will just be 0. And I'm saying I'm going to set this equal to 1/2 after I plug this in. So I'm plugging in m. I'm going to get 6/5 m minus, I'm going to plug in here, I'm going to get m squared over 5. And that should end up equaling 1/2. And again, really, I'm plugging in the 0. I'm doing 6/5 m minus m squared over 5, and then I'm subtracting when I plug in 0, but all the zeros give me nothing. So I'm trying to solve this equation for m. And this is definitely looking quadratic to me. Now, I could use, and I will probably use the quadratic formula, but I would like to make my life easier. So let me write this on the other side, because I want to kind of show you how to make this not as terrible as it is. So there's definitely ways to make our lives easier here. So let's see, I've got the equation 6/5 m minus m squared over 5. And there's a couple things I would do. The first thing is I would actually bring everything to the right, because I would prefer to have my m squared coefficient be positive. So I write this on the right, it's going to be 0 equal to positive m squared over 5 minus 6/5 m plus 1/2. Now you could totally use the quadratic formula here. You could say, I'm gonna use the quadratic formula where my a value is 1/5, my b value is negative 6/5, and my c value is 1/2. And that's gonna suck, right? Like, I don't wanna do that. We totally could. I could write it out and it's gonna be awful. I don't even really wanna write it out. Here's what you should do, in my opinion. If I know I'm gonna have to use the quadratic formula when you're trying to solve a quadratic equation equal to 0, I can get rid of the fractions. I can multiply both sides by whatever number I want that's not 0. So I'm gonna multiply both sides by the common denominator, which is 10. This isn't gonna change my answer, but it's gonna make it a lot easier to find, because now 10 times 0 is still 0. When I distribute the 10 here, 10 times m squared over 5 is 2m squared. 10 times negative 6 over 5, all the 10 and the 5 cancel, be a 2. And 2 times negative 6 is negative 12. And 10 times 1/2 is 5. And to me, at least, this is going to be a little bit easier. Now, let me double check. I feel like, Nicole, maybe you made a small error. You did make a small, oh no, you did something slightly different, which is also perfectly good. Yeah. You did the same kind of thing. Your work is the same, Nicole. Well, not the same, but you arrived at the same place almost. So from looking at, so just so everyone can see, I'm going to share your work if that's okay with everybody. If that's okay, Nicole, I'm going to share the work. Well, yeah, you posted it. You already shared it. I'm going to share it. So here's what Nicole did, which I think is great, right? She was solving this. She had the 1/5. She factored out the 1/5, which is smart, I think. And then she multiplied both sides by 5, which I would totally do. And then at this stage here, I would take the additional step. Instead of having to deal with this negative 5/2, I would take the additional step of multiplying everything by negative 2 to get positive 2m squared minus 12m plus 5, because that's just going to make things a tiny bit easier. I really try to avoid the fractions in my quadratic formula if I can help it. I will also say this might factor. We could try to factor it, but if I don't know how to factor it, I don't really want to waste time trying to. So I'm just going to go to the quadratic formula. So let's see. I know that my m is going to equal negative b. Oh, so here instead of these numbers, I'm using a equal to 2, b equal to negative 12, and c equal to positive 5. Yeah. Yeah, okay. Which is just all of these numbers multiplied by 10, right? 1/5 times 10 is 2. This times 10 is negative 12. This times 10 is 5. So I'm going to get negative b, so 12 plus or minus the square root. Oh, I think this is going to work out nicely. B squared, so 144 minus 4 times a times c. That's not going to work out so nice. That's fine. All over 2 times a. Simplifying. I guess I thought this factored, but it doesn't. You get 12 plus or minus the square root of 144 minus, let's see, 4 times 10 is 40, so that's 104 all over 4. So the problem here is that there's 2 answers, but there should only be 1 median. So we have to pick the answer that makes sense. Is it 12 minus 100 square root of 144 or 12 plus square root of 144? So here's what I would say. And so it's possible that both these answers are in the interval from 0 to 1, but that's what I'm actually looking for. I'm looking to see if only one of these is between 0 and 1, that has to be the median, because the median has to be the answer between 0 and 1. Right? The median can't be outside of the interval. So I could get out a calculator. That's probably what I should do. But here's what I'm going to do first. I'm going to say, well, square root of 104 is about 10, right? So I can say my answers are about 12 plus 10 over 4 and 12 minus 10 over 4. 12 plus 10 over 4 is 22 over 4, which is about 5.5. That can't be the answer. It's too big. Our answer has to be between 0 and 1. Boom. So we know it's got to be this one. And it makes sense, right? 12 minus 10 is about 2, is 2. 2 over 4 is 1/2. So the one where it's minus is the correct answer. 12 minus the square root of 104 all over 4. And this actually simplifies a little bit. 104 does have a factor of 4. 104 is 4 times 26. So you can rewrite this as 12 minus The square root of 4 is 2, so we bring the 4 out as a 2. 2 root 26 all over 4. And then you can cancel a 2 from everything. 12 divided by 2 is 6. 2 divided by 2 is 1. This is probably the most simplified version of the answer. But there is only one answer. So more generally, right, if you see yourself getting 2 answers for a median, one of them often will be outside of the domain of possibility. That's a good question. I like this one. It definitely makes you think about what's happening. So, are there questions about this?
What happens if both of them are in the domain?
I was afraid you were going to ask that. That's a good question. I don't know if I have a good answer. Yeah, I feel like that shouldn't be possible. And here's why. If we're solving, right, so again, if we go back to the kind of idea, right, if we're trying to find, right, the place where, if we're between A and B, where the area is 1/2, there should only be one value where half of the area is on the left and half of the area is on the right, right? It shouldn't be possible for there to be 2 distinct numbers that exactly cut this region or this area in half. So my intuition is that it should never happen that both of the answers come up in the interval. It should be impossible.
Okay, that makes sense.
Although I think it would be challenging to prove that, maybe from just a looking at the picture kind of idea. I think it's fairly intuitive that it should be impossible for there to be 2 answers. But I do think that's a good question.
I have a question, not about this, but like, is there any way, if not, it's okay, because I know that it's kind of soon, that you could make a review sheet for FAM's class since our midterms on Friday?
Midterms on Friday, okay. And so, I mean, yes, but I think also I should do that for both of you guys' classes.
Okay.
Because obviously you guys have very different things going on. So what I'll most likely do is I'll look around, because we definitely have review sheets that we've already written in the past, and I'll try and cull some problems for both FAM and MERCS. Some of it will obviously overlap, but clearly the MERCS class is doing some extra things, so I'll try to throw those in. I'll try to make separate sheets so that the people for the MERCS class can have some extra problems doing surface area and arc length, which I imagine we will definitely talk about next week on Tuesday, because I imagine I should make some surface area, because I know you guys are going to cover surface area, because he said it, or he didn't say it, but he wrote it in the notes. So I should make some surface area and arc length videos, because I'm sure you'll have questions about that stuff before class on Tuesday. Give me just 1 second. I need to grab some water because I forgot to get it. So I'll be right back. Think about some questions. I'll be back in a second. It is definitely warm in Woodland today. And Davis. It's supposed to cool down tomorrow, though. All right, so for the FAM folks, are there other questions or things you would like me to talk about?
Could you do a probability density function where one of the limits is infinity, or the?
That's exactly what I was about. excellent question. Good leading question. So what you're specifically referring to is one of these special probability density functions, specifically the exponential one. So let's say we have, sorry, let me find, yeah, okay. So let's see our function looks like this. So let's say we have f of x equal to, what have I got here? Let's do this, sure. 1/8 e to the negative 1/8 x on the interval from 0 to infinity. And so more generally, or you can write it like this, or you can say, you know, x is between 0 and infinity. These functions always look like, these exponential ones always have the form some number times e to the negative of that number times x. So if you look in your book on page 638, the general form of this is generally f of x equal to a times e to the negative ax on the same interval. And so I should say the nice thing about these is, well, we always know what the answer is going to be if we remember. So you can, for this one specifically, you kind of memorize what the mean and the variance are. We're going to calculate it. It's going to be a little bit of a pain in the butt, but it's worth kind of seeing how the calculation works. So let's find the mean. I feel like the median is kind of challenging, so maybe we won't do the median. We'll see. So let's do the mean. Calculate the mean, right? It's going to be the integral from 0 to infinity of x times 1/8 e to the negative 1/8 x dx. Did I want to say anything about that? Not really. I suppose I should show you guys it actually is a PDF, meaning that the area under the curve should actually equal 1. So let's do that first, and then we'll come back to this. It's good to see all the things. I'm wearing slippers, but my feet are too hot. So to show it to PDF, sorry, so f of x is the function 1/8 e to the negative 1/8 x. So first of all, if someone asked you to show something was a PDF, right, on the interval from 0 to infinity, there are two things you would have to say to show something as a PDF. Not that I think you will necessarily be asked to do this, but here's what I would do if I was asked to do this. First thing, you have to show, or really just say, that the function is bigger than or equal to 0 on the interval. And we know this is true because e to the anything is always positive. So I don't think there's really, oh my God, sorry, I'm just like, oh, my hair looks super crazy. Gotta stop the math, it's not a big deal. Okay, so, yeah, so he was a good teacher, but he talked about his hair all the time. Okay, I hear my wife laughing with me. This is always positive. We know it's always positive because e to the anything is always positive. Or any positive number as a base is all to the next one is always positive. So that part's easy. The second part, which is the part that I can actually imagine someone asking you to do, is to show that the integral on the interval of the function is equal to 1. So let's do that. So we're going to do the integral from 0 to infinity of 1/8 e to the negative 1/8 x dx. And of course, for this one, we have to use a limit. So that's going to be the limit as t goes to infinity of the interval from 0 to t of 1/8 e to the negative 1/8 x dx. Okay, integrating this is not terrible, right? We know the integral of e to the something times x is e to the something times x divided by that something. So check this out. We're going to get the limit as t goes to infinity. The 1/8 is just going to hang out. And the integral of e to the negative 1/8 x is e to the negative 1/8 x divided by the coefficient of x, which is negative 1/8. Right, that's always going to happen when you have just e to the constant times x. Right, just like the integral of e to the 2x is e to the 2x divided by 2. And again, the rationale there is because the derivative, you have to use the chain rule and multiply by this coefficient. If the derivative of e to the negative 1/8 x is e to the negative 1/8 x times negative 1/8. So we need this negative 1/8 down here to cancel it out. And the nice thing is, of course, this simplifies. Right? The 1/8 here and the negative 1/8 here essentially cancel out, leaves the negative 1. So that cancels, and we get the limit as t goes to infinity of negative e to the negative 1/8 x from 0 to t. There is one more simplification I would do before plugging in my limits of integration. I really, really don't like negative powers for my exponents. So I would rewrite this as negative 1 over e to the positive 1/8 x. For me, it's just easier to deal with. And I think it is for most people. So I would write this as the limit as t goes to infinity of negative 1 over e to the positive 1/8 x from 0 to t. And you could probably have plugged in your t and your 0 already if you wanted to. So now this is the limit as t goes to infinity of negative 1 over e to the 1/8 times t minus negative 1 over e to the 1/8 times 0. Okay, t goes to infinity, 1/8 times t goes to infinity, and e to the infinity goes to infinity, and 1 over something that's really, really big is going to be going to 0. So you get 0 minus, well, I get 0 minus minus is 0 plus 1 over e to the 0 is 1 over 1. So as expected for this probability density function, the area under the curve on the interval is just 1, and that should always be the case. Okay, questions about this? Let me look this thing here. Yeah, okay. So something else to know. We're going to do this calculation, but I imagine, well, I actually don't know. What we're going to see for this calculation is that the mean is going to be 8. Or more generally, the mean for any probability density function like this, is going to be 1 over a. Oh, what does the bottom line say? Sorry. Bottom line says the limit as t goes to infinity of negative 1 over e to the 1/8 t, and that part's going to 0 because the bottom's going to infinity, minus negative 1 over e to the 1/8 times 0. This e to the 1/8 times 0 becomes e to the 0, which is just 1. So you get 0, right, that's 0, minus a minus, so plus 1 over 1. That's what we're getting there.
Thank you.
Of course. So I think most of the time, professors kind of, when they ask you about this, I think they just expect you to memorize or use the fact that for this type of probability density function, the mean is just 1 over whatever this coefficient is here. So I know the mean here, I'm going to show the work still, but I know the answer is going to be 1 over 1/8, which is just 8. Or generally 1 over a. And then you guys have to remind me, I imagine the answer is yes for Merckx's class, but have you guys talked about L'Hopital's rule? I don't remember. No. Is that a no for both classes? I imagine it's probably no for both classes. Okay. So the big old no for, okay, so then we'll kind of do what I call like the kind of hand wavy version of this. So for this integral here, we have to do integration by parts, which I know is not everyone's favorite, but it's not terrible. It's just a one-step integration by parts. For the variance, it is a two-step integration by parts, and that's what things get kind of really messy. So for the mean here, we're going to do integration by parts. we're going to let u equal the 1/8 x. You can just do the x, but we might as well throw the 1/8 in there because it's going to work out nice. Sure, why not? I'll just do it that way. So u is 1/8 x, and my dv is the rest. It's the e to the negative 1/8 x dx. My du is 1/8 dx. And my v, the integral of e to the negative 1/8 x, is e to the negative 1/8 x divided by negative 1/8. Or times negative 8. Oh, by the way, just in case, make sure everybody got it. Here's the attendance again. Whoops, that's not. There it is. Okay. So just doing the integral without actually doing worrying about the limits of integration yet, we're going to see that the integral of x times e to the negative 1/8 x dx is equal to, I thought I had a good blue pen here. So there's a black pen. Is equal to u times v, so 1/8 x times e to the negative 1/8 x over negative 1/8. The 1/8s are going to cancel out, minus the integral of v du. So e to the negative 1/8 x over negative 1/8 times 1/8 dx. And this becomes a lot simpler, right? Dividing by negative 1/8 is like multiplying by negative 8. So the 8s will cancel, and you'll get negative x e to the negative 1/8 x minus a minus is plus the integral, and again, the 1/8 and the 1/8 will cancel. So you plus the integral of e to the negative 1/8 x. So this ends up equaling negative x e to the negative 1/8 x. The integral of e to the negative 1/8 x is e to the negative 1/8 x divided by negative 1/8, or times negative 8. So minus 8 e to the negative 1/8 x. So that's what the integral of that looks like. We could use the tabular method as well. Yeah, tabular would be fine here. I often, when it's just a one-step integration of my parts, I typically don't use the tabular method just because, I don't know. But yeah, it would be totally fine to use the tabular. And you can take the 1/8 out or not. You could also include, right? You could, if you're doing tabular, you could let your u be just 1/8 x, and that would also work out just fine. In fact, why don't I show that, since we might as well see it. So you can totally do it the way I just did it, or you could definitely use tabular. Right, so if we're looking at this, I could definitely use tabular, where I'm gonna, oh, sorry, not that. No, looking at that. I don't think there is a 1/8 to take out, sorry. Yeah, so if I'm letting, sorry, my brain just, oh, I think, my brain did something. I think there definitely was a 1/8. Yeah, there should. Sorry. I erased too quickly. I don't know what's happening here. I think this was supposed to be something else. Sorry. We definitely were looking at the integral of. Sorry, guys. We were looking at the integral of x times f of x. So that was the integral of x times 1/8 e to the negative 1/8 x. Apologies. And you can either bring the 1/8 out or not. I'm going to call this my u, which is definitely what I did here. And this my dv. So you could do tabular. U is 1/8 x. The derivative of 1/8 x is 1/8. The derivative of 1/8 is 0. My dv is e to the negative 1/8 x. The antiderivative of that is e to the negative 1/8 x divided by negative 1/8 is the same as multiplying by negative 8. And then the antiderivative of that is going to be, again, e to the negative 1/8 x. I'm going to divide by another factor of negative 8, I'm going to divide by another factor of negative 1/8, which is going to multiply by another negative 8. So I'm going to get another negative 8, and you're going to get 64. and then to be this and this plus. So it's going to be, when I multiply this times this, so here's what I'm going to get. I'm going to get 1/8 x times negative 8 e to the negative 1/8 x. And I'm going to get minus 1/8 times 64 e to the negative 1/8 x. Which should be exactly the same as this. Right here, the 8 and the 8 will cancel. And I'll get negative x e to the negative 1/8 x, which is exactly what I have there. Here, the 8 and the 64 will reduce to an 8. I'll get minus 8 times e to the negative 1/8 x. So yes, either way should work fine. So now, to actually calculate the interval we wanted to calculate, which was, go to the other side here. Sorry, I know this is kind of a little messy for what we're getting at, but it's not the worst thing ever. So we're trying to find the integral from 0 to infinity of x times 1/8 e to the negative 1/8 x. We calculated the integral, so it's going to be the limit as t goes to infinity of the integral from 0 to t, and then we're going to integrate, and we're going to get the integral from 0 to t. But the integral is just what we did, right? It's this. It's negative x e to the negative 1/8 x. And then it's minus 8 times e to the negative 1/8 x. Now, I would do something that I always do. I'm going to make my negative exponents positive. So I'm going to rewrite this as negative x over e to the positive 1/8 x. And we write this as 8 over e to the positive 1/8 x. And now I'm going to plug in my limits of integration. So the limit as t goes to infinity of plugging in t, I get negative t over e to the 1/8 t minus 8 over e to the 1/8 t minus, plugging in 0 here actually is important. It doesn't give us just 0. I get 0 over something. Okay, that is 0, right? Negative 0 over e to the 0 minus 8 over e to the 0. So now here's what happens. This is where we would normally use L'Hopital's rule, but we don't have it. So this part here, well, t is going to infinity. E to the infinity is going to infinity. And so if we're dividing by something that's infinitely large, it's going to get infinitely small, or infinitesimally small, I should say. Whoops, it's not going to infinity, it's going to 0. Now here you can kind of apply the same reasoning, except the top is going to infinity and the bottom is going to infinity. What we say here is that the bottom is going to infinity much, much faster, right? E to the something gets infinitely large way, way faster than t does. In fact, if we look at the, I mean, I feel like you guys believe me, but let me show you just in case you don't believe me. Graphing Desmos. So let me share my screen. That's not what I wanted. So if we graph these, so I'm going to compare, I'm going to do positive t just because I don't really care about the minus sign there. Let's just bring this minus out in front. If I compare the graph of y equal to t versus y equal to e to the 1/8 t, which I'm just writing as t over 8. So at first it looks like the y equals t function gets bigger faster, but if we zoom out, right, I mean, look, the blue function gets bigger so much faster, it's not even close to being comparable, right? Just when you're getting over to like maybe 200, right, e to the 200 over 8 is super, super big, whereas, you know, if you're plugging 200 to the red function, you're just getting 200. So the blue function is so much bigger than the red function. Then it makes sense that this fraction is getting infinitesimally small as well. And that's always going to be true for any polynomial over an exponential function, is the exponential function is always much, much bigger. So the fraction always eventually goes to 0. This could be t, it could be t squared, it could be t to the 18th power. This bottom thing is always going to overpower it. So here's what we end up getting. We get minus 0 minus 8 over 1. So we get negative 0 minus 8, which is 8. And that's what we expected to get, right? Because we said way back in the beginning, I think I erased it. Yeah, we said way back in the beginning that for f of x equal to 1/8 e to the negative 1/8 x, the mean should be 1 over 1/8, which is just 8. So I don't know if your teacher expects you to do all this work to find the mean or the expected value. Oh, there's a pun in there. I don't know if your teacher expects you to do all this work to find the expected value. But, sorry, that was a late pun. But this is how you would do the work if you had to. And then I really can't imagine they'd expect you to find the variance. So here's how you find the variance. Let me go to this side. So I'll show you the beginning of finding the variance, but I don't think it's something you should actually do because it's just more of the same. I can maybe do a quick version of it if you guys want me to. So
sorry. For that one, when you're plugging in, like for when it was like infinity over bigger infinity, so it still goes to 0. Does it matter that the top was like negative t, like that it's negative infinity?
It does not matter at all. The sign, if you're going to 0, it doesn't matter if it's a negative or a positive.
Okay.
Yeah. Because again, yeah, it doesn't matter.
So for this problem, we knew that it was 8 like at the beginning because it was infinity at the top, right? So then that gives you like
I would say we knew it was 8 specifically because it's a very specific type of probability density function. It's an f of x equals something times e to the negative something times x, right? This number here and this negative number here are opposites of each other on a 0 to infinity. But what I'll say more generally, now, someone could totally make up a probability density function that wasn't this. But if it looks like this specifically, then we know that the mean is 1 over a. However, I could totally make up a different function that's totally not like this. It still has an infinity on it. For example, and so here's one off the top of my head that I know is true. This function, 1 over x on the interval from 1 over x squared, sorry, on the interval from 1 to infinity is also a PDF because the area under the curve is exactly 1. And this would have a different mean. In fact, that would probably be a good question. What's the mean of this function on this interval? It's definitely not going to be, well, right, so this one isn't of the same form, right? It's not just going to be 1 over a. There is no a really. Let's actually do this question. It's not terrible. In fact, it's much, much easier than the one we just did. I could totally see someone asking a question like this because it's not really out of the realm of possibility. So first we could show it's a PDF. I don't really want to do that. We could. The way we took the PDF is you find the integral from 1 to infinity of 1 over x squared dx. And you would get that it was equal to 1. Here's the work we would do. Limit as t goes to infinity, integral from 1 to t. I'm going to rewrite this as negative x, sorry. I'm doing the integral already accidentally, as x to the negative 2. We integrate. And we get x to the negative 1 over negative 1 from 1 to t. I'm going to rewrite this as 1 over negative x or negative 1 over x. Right, it's negative, I don't care if it's on top or bottom. I'm going to write it like that. So then plugging in the t, plugging in the 1, and t goes to infinity, 1 over t goes to 0, minus 1 over 1 is 1. So great. We showed it to PDF because, well, I didn't actually show it to PDF. I showed the area under the curve was 1. And then it's also, I think, relatively obvious that 1 over x squared is always going to be non-negative, right? It's always greater than or equal to 0. It's actually always positive unless it's undefined. So great. That shows it's a PDF. How am I going to show its, or how am I going to find its mean? This is good. This is a good question. Good job, James. Way to find it. Here I am, patting myself on the back. All right, so to find the mean of this function f of x equal to 1 over x squared on the interval from 1 to infinity, we're going to do the integral from 1 to infinity of x times the function, which is also, holy smokes. Did I just come up with something stupid? Oh, I did. This is a dumb question. So, wow. That's really interesting. Huh. This function doesn't have a mean, I guess. Huh. I don't know. I feel stupid. It's okay. Sometimes we do dumb things. So so you guys might not be seeing it yet. You're about to see it. So I'm trying to figure out what the mean is. And this is how you would calculate the mean, supposedly, right? But the problem here is that if you do this, this is 1 over x. And we're going to do the limit thing, right? So the limit as t goes to infinity of the interval from 1 to t. And then we integrate this. Look what happens. The interval of 1 over x is the natural log of the absolute value of x from 1 to t. If I do this, this is weird. The natural log of t minus natural log of 1. But as t goes to infinity, the natural log of t also goes to infinity. So what this means is, although this would be a PDF, right, you've got right, this function 1 over x squared looks like this. And the area under the curve is definitely finite, right? It's definitely 1. The mean or the expected value is infinite because here the way it works is you've got this tail that's infinitely long, and it happens that you have kind of an infinite amount of area. Well, not infinite, it's a finite amount of area, but the way the area is distributed means that you've got this kind of really heavy tail. Whereas that's not the case. So the problem with this particular function is it doesn't get small fast enough. Whereas f of x equal to 1/8 e to the negative 1/8 x gets small really, really fast. So that's kind of the difference. So this would be a bad question on the test. If someone asked you to find the mean of this particular function, they would be a jerk because you can't find the mean, or I mean, the mean is infinite, literally. There isn't a mean. Yeah, okay. So back to where I was before. Sorry, I got sidetracked. I can actually think of a good question, which I might ask you guys in a second. So what I want to answer, whoever said it, is just because you see an infinity doesn't mean it's always going to be 1 over a. It has to be this specific format. However, or not however, additionally, we could find the variance. Now, I don't want to do the work finding the variance, but here's the setup to find the variance. To find the variance of this particular function, right, the way you would do it, and again, we know the mean already is 8. The way you should find the variance in general, even if it's something that's easier, is you should do the alternate formula, where the variance is the integral from 0 to infinity of x squared times your probability density function minus the mean squared, which in this case is 8 squared. Right, that's the easier version. The harder version is where you do x minus the mean quantity squared, and then you end up multiplying it out. That's much, much worse than that, especially in this example. And for this particular probability density function, the variance always ends up being, I believe it is your a value squared. Double check that. Or sorry, 1 over a squared. So yeah, it's going to be 1 over 1/8 squared, which is going to be 64. we could calculate this one. I would definitely use the tabular method here. It's going to be kind of gnarly though. And I mean, I would like to think that they're not going to be asked to actually do this, but I don't actually know. So do you guys want me to do this variance calculation or not? Does anybody vote yes for we should do it? It's really fine if it's all no's. Okay, thinking that's going to be a solid no from everybody. This is how you would, oh, okay, that's fine. Let's go. So here's how you calculate this. And again, I would definitely use tabular. That's fine. I'm happy to do it. I just didn't know if everybody wants to see it. But then I will actually come up with a good infinite one. It is not the one I thought I had a good one, but yeah, I've got a better one though. Oh, yeah, I got a really good one. So here's how we do this, right? So it's the integral of x squared times 1/8 e to the negative 1 over 8x dx. Let's leave off the limits of integration for now. So I'm just going to do I always do the antiderivative before trying to deal with limits. I mean, I'm going to take someone's advice and put the 1/8 on the outside, so I don't have to deal with that. So my answer is going to be 1/8 times whatever the tabular method gives me here. So the tabular method, I'm going to let u equal x squared, and then the derivatives are 2x and 2 and 0. And my dv is going to be e to the negative 1/8 x. And each successive antiderivative is going to divide by negative 1/8, which is like multiplying by negative 8. So my first antiderivative is going to be negative 8 times e to the negative 1/8 x. My next antiderivative is going to be positive 64 times e to the negative 1/8 x. My next antiderivative is going to be negative 512 times e to the negative 1/8 x. And actually, I would prefer to rewrite all of these as well. I would prefer to rewrite this as 1 over e to the 1/8 x. And this as negative 8 over e to the 1/8 x. And this as positive 64 over e to the 1/8 x. And this as negative 512 over e to the 1/8 x. Okay. So let's say everything's going to be negative, right? Because it's this times this, it's minus this times this, it's plus this times this. So here's what I'm getting. I'm getting x squared times negative 8 over e to the 1/8 x. So I'll write that as negative 8x squared over e to the 1/8 x. I'm getting 2x times, or minus 2x times 64 over e to the 1/8 x. So it's going to be 128x, sorry, minus 128x over e to the 1/8 x. And then finally, 2 times 512 is 1024, so minus 1024 over e to the 1/8 x. Okay, here's what's going to happen. So if we actually do the limit, right? So I don't want to write all this again. That's the problem. I'm going to erase this here. So if you need to see it, it's about to go away. But you can always go back and look at the video later. Okay, I'm not hearing anyone telling me to stop, so I'm going to erase it. Okay. So I'm actually doing the integral, right? So the 1/8, the integral from 0 to infinity, sorry, infinity of x squared e to the negative 1/8 x dx equals the limit as t goes to infinity of the interval from 0 to t of the same thing. I'm going to go ahead and write the integral, and I'm going to plug in t and then plug in 0. Here's what I'm going to get. I'm going to get the limit as t goes to infinity of 1/8 times, plugging in t, you get negative 8t squared over e to the t over 8 minus 128t over e to the t over 8 minus 1024 over e to the t over 8 minus, and I plug in 0, and I get 0 minus 0 minus not 0 minus 1024 over e to the 0, which is 1. I'm worried about my numbers a little bit, but not enough to be too worried. And it's possible I made an error somewhere. I don't think I did though. Okay, so let's see here. So here's the thing. Just like we said before, each of these things is going to go to 0 because I have a polynomial thing over an exponential thing, and the exponential thing gets infinitely large way faster. So this goes to 0, this goes to 0, and this goes to 0. So I'm left with, there's no negative here. That's crazy. Sorry about that. I'm left with a 1/8 times 1024. And I feel like I'm off by a factor of 2 somewhere, because 1/8 over 1024 is 128. And my answer should have been 64. Damn it. So close. So yeah, it should have been a 1/8. I accidentally threw in a negative sign there. I don't know why, Sophia. Well, darn it anyway. Why am I off by? Oh, because this isn't the variance. I forgot to subtract my mu squared. Right? This is the integral we're calculating, but the variance is going to equal the integral from 0 to infinity of x squared e to the negative 1/8x dx minus the mean squared. So that's going to be 128 minus 8 squared, which is 128 minus 64, which is 64. Check. Yeah. So it feels good to figure out your mistake in the least terrible way possible. Okay. Let's do one more. Let's do one more that's left. So again, here's what I'll say about this, right? So for this particular special distribution, which I think is the most challenging of them all, because the normal one, no one's ever going to ask you to calculate because you can't really. And the uniform one we'll talk about next time is super easy. It's straightforward. It's just a rectangle. But this one, the nice thing about this one is that the mean and the standard deviation are both the same. Here the mean is 8. Here the variance is 8, which means the standard deviation is the square root of 64, which is also 8. The median, yes, we definitely could do the median. Excellent question. That's not disappointing to hear my voice. It's just, no, it's not disappointing. I'm just like, oh, the median is probably the hardest. Not the hardest. Let's calculate the median. So again, you definitely should use the 0, right? Not the, yeah, you should definitely use the 0. So we're going to do the integral from 0 to m of 1/8 e to the negative 1. The median here is actually not terrible at all. So this one's pretty straightforward. We're setting this equal to 1/2, of course. So integrating this, we just get negative e to the negative 1/8x. Right, because the integral of this is e to the negative 1/8x divided by negative 1/8, and the 1/8 over negative 1/8 is e to the negative 1. And this isn't too terrible at all, actually. So I'm going to get negative e to the negative 1/8 m minus negative e to the negative 1/8 times 0 equal to 1/2. So I have negative e to the, I'm going to write this as negative m over 8 plus 1 equals 1/2. Subtract 1 from both sides. I've got negative e to the negative m over 8 equals negative 1/2. Change both sides to positive. So I've got e to the negative m over 8 equals positive 1/2. Take the natural log of both sides. And then notice the natural log of 1/2 is negative. So negative m over 8 multiplied by 8. Negative m equals the natural log of 8 times natural log of 1/2. And then m is negative 8 times natural log of 1/2. Or you can bring this negative 1 up as a power. Right? You can say this is 8 times natural log of 1/2 to the negative 1, which is just 8 times the natural log of 2. And I'm pretty sure that for any of these types of functions, so for f of x equal to a times e to the negative ax on the interval from 0 to infinity, I believe the median is always equal to a times natural log of 2. Don't think they say that in the textbook, but I'm almost 100% positive. We could totally show it. Let me just double check.
Would it be 1 over a? Because wasn't a...
Oh, yeah, you're right. Good call. Yeah, excellent. I always forget. Yeah. Good. Then, so, yeah. You're right. I feel like it's probably a homework problem somewhere in that section, but who knows? Anyway, let's do one more of these. So these ones with infinity as a limited integration are always kind of a pain, but let me give you guys another. Let's do one more question like this. Well, not exactly like this. So again, I'll reiterate. I would like to imagine no one's actually asking you to calculate this. It's kind of an unfair ask because technically it really does require L'Hopital's rule, although you can be hand wavy about it. But someone could ask you to calculate the mean of this. I feel like the variance is kind of exceptional, so just be aware that those particular functions, right, there is just a way to think, oh yeah, I know that the mean is just 1 over a. The variance is 1 over a squared, which means the standard deviation is also 1 over a. And yeah, and then finding the median is actually not terrible at all. So let's say we have this. So here's the question. Find the constant k so that f of x equal to k over x cubed is a probability density function on the interval from 1 to infinity. This is definitely a type of question people like to ask. So if you want something to be a probability density function, first of all, it has to be non-negative, which this will be as long as k is positive, which it probably will be, which it definitely will be. The second thing that has to be true is the integral on the interval of the probability density function. If it's a probability density function, this has to equal 1. So the first thing we have to do is actually solve for k. And then after we do that, and then find the mean. I think I get to reward myself with a new black pen. Oh, I got a perfectly red pen over here. Red's fine. So the way we're going to do this is we're going to just do what we usually do. To have the limit as t goes to infinity of the interval from 1 to t. I'm going to write this as k times x to the negative third. Do the integral as t goes to infinity. Integral of k times x to the negative third is k times x to the negative 2 over negative 2 from 1 to t. I personally always like bringing my negative signs up, right? So I would write this as negative k x to the negative 2 over positive 2, or really I'd write it as negative k over 2x squared. That's my preferred way of writing it. You can do whatever you like as long as it's correct, right? Which is usually true, right? So this is negative k over 2x squared. I just like my powers to be positive, but I like my negative coefficients to be on top or out front. Okay, we're plugging t. Remember, we're plugging in for x. So this is the limit as t goes to infinity of negative k over 2t squared minus negative k, so plus k over 2 times 1 squared, which I'm just going to write as 2. Don't need that anymore. This is going to go to 0, because no matter what constant k is, k over something that's going to infinity is going to go to 0. So k over 2 is going to have to equal 1, so k has to equal 2. That's a k. I know you might not believe that's a k. It's a k. So our PDF is actually the function 2 over x cubed on the interval from 1 to infinity. And then we combine the mean. And maybe even the variance. The variance, I don't know. Variance might be, we might run into the same problem we ran into before. Of being infinite in some way. So the mean, which is why I think we probably usually do over x to the 4th. So if our function is 2 over x cubed, the mean is going to be the integral from 1 to infinity of x times 2 over x cubed dx, which is 2 times the integral from, let's do a limit. Can I do a limit? It is, I will say, if your teacher is asking you to show work, right, and they're giving you credit for showing work, which may or may not be the case with FAM, because there's a lot of multiple choice stuff. But if they're asking you to show work, it really is important that you show that this limit, t, or whatever letter you want to use, goes to infinity of the integral from 1 to t. I'm going to write this as 2 times x to the negative second. Because x over x cubed reduces to 1 over x squared over x to the negative second. Now we're going to integrate. The limit as t goes to infinity. This is going to be 2x to the negative 1 over negative 1. And I would personally prefer to rewrite this as negative 2 over x. Now I plug in my limits of integration, and I get negative 2 over t minus negative 2 over 1. And then as t goes to infinity, this goes to 0. So I get negative 2, which is positive 2. So my mean happens to be 2 here. And yeah, I don't think we can find the variance for this because I think we run into the same problem where if we were doing the variance, we'd have x squared times this, and then we'd have 2 over x, which would integrate to 2 natural log of x. And then we have an infinite thing. So I don't think you can find the variance or it's unknowable for this. Maybe it's, I feel like it's either unknowable or it's infinite, but again, I wouldn't worry about this one. So I could see, in fact, this might be, I'm going to give you guys not homework, but I'm going to give you a problem to work on, and then maybe I will post a video of this problem later on. I would say I want you to do the same thing for this function for f of x equal to k over x to the 4th on the interval from 1 to infinity. I would like you all to, if you think this is valuable for you to do, right? If you think your teacher's not going to ask about this, I would leave it away. But for this function, I think you guys could all find the mean and the variance, because this one, the variance won't be stupid. And you could also even find the median. So if you're looking for something, some practice of one specifically with infinite limits of integration, try that out, because I think that would be a good problem. And I will definitely, I'll make a video of that later today. And yeah, and I will show you how that works. I probably won't do a video of I can do another exponential one. I just will probably not try to get too detailed. Ooh, it's definitely warm in here. I wonder what we have the AC set to. Not low enough for me. All right, what else do you guys want to hear about in the last 7 minutes we have here? Or are there questions about this? AC real quick. I guess it was already set pretty low, 76, so I can't complain too much. So was something I had. Oh, I know what it was. So not everything is infinite. I mean, obviously, you could totally ask questions like, so here's a function. Oh, that's terrible. Look at that one, James. So here's something that seems kind of ridiculous. This is just problem from a textbook. It's the problem 36. The function, the probability density function is 3 over 256 times x minus 2 times 10 minus x. And we can ask questions like, on the interval from 2 to 10. And we can ask questions like, find the mean, find the variance. Someone could just easily say, find the standard deviation, right? If you're finding the standard deviation, you're just finding the variance and then taking the square root. And we can also ask something like, what's the probability, that's a dumb question, what's the probability that x is bigger than or equal to 2 and less than or equal to 4. Yeah. Oh, and I have median too, sure, why not? We probably don't have enough time to acquire all this, but whatever. So first of all, let me point out that it is a PDF. I'm not going to do the interval to show it's equal to 1, but I'm going to point out that this function is definitely negative outside of this interval from 2 to 10. If you plug in anything less than 2, like 1, this part's going to be negative. If you plug anything bigger than 10, this part's going to be negative. So it's definitely only non-negative on the interval from 2 to 10. Let's find the median. So I'm going to put the 3 over 256 on the outside. Iterate from 2 to 10 of x times x minus 2 times 10 minus x. And yes, we should definitely multiply this out. This is going to be 3 over 256 times the integral from 2 to 10. Let's see. This part here is, I have a negative x squared. I have a positive 2x plus 10x is a plus 12x. And I have a minus 20. So multiplying that all by x, I get negative x cubed plus 12x squared minus 20x. So let's see, I get 3 over 56 times. Integrating this, I get negative x to the 4th over 4 plus 12x cubed over 3 is going to be 4x cubed minus 20x squared over 2 is going to be 10x squared. These numbers do not look great. I would probably get a calculator out. Yeah, this looks kind of gross. Sometimes the numbers are gross. That's just the way it goes. So negative, so I get 3 over 256. Negative 10 to the 4th is 10,000. Negative 10,000. 4 plus 4 times 10 cubed is 4,000. Minus 10 times 10 squared is 1,000. And then 10,000 over 4 is 2,500. Okay, these numbers aren't turning out so bad so far. Minus, I plug in 2. 2 to the 4th is 16. 16 over 4 is 4, so I get minus 4. 2 cubed is 8 times 4 is 32. 2 squared is 4 times 10 is 40. Okay, this could have been worse. So I end up with, let's see, 4,000 minus 1,000, 3,000 minus 2,500 is 500 minus 32 minus 40 is negative 8 minus 4 is negative 12 minus a negative 12 is plus 12. Oh, this works out really nice. I get 3 over 256 times 512. 512 over 256 is exactly 2. So I get 3 times 2, which is 6. Which is not surprising to me because this is a parabola. In fact, so there's actually some nice graphicalness here that I should tell them about. So this function is quadratic. It's a parabola. And it's got an x-intercept at 2 and positive 10. It looks like this. Or vague. You know what? Gradescope is an awesome tool. Why am I trying to graph? So here's what I should say. Gradescope is a great tool. You should definitely be able to graph something like that without doing too much work. But Gradescope is going to make it look nicer. And I can do exactly what I want. So let me share my screen with you. Let me graph this thing real quick. So I've got, what do I got here? 3 over 256 times x minus 2 times 10 minus x. That doesn't look like what I want. What are they doing? Your y equals here. That's dumb. So sometimes Gradescope is dumb, or not Gradescope. Desmos. I said Gradescope before, I think. What's going on here? You know what? It's just ha ha ha. So here's the problem. It's not that the intercept is 0, although it totally looks like it's 0. It's then zoomed way too far out. And here we actually are. So the problem really is the 3 over 256 is making it really, really flat. I'm going to take away this 3 over 256. I wonder if there's I feel like there's a way to like change the y scale or just the x scale. But I don't have enough time for that. So here's what I'm going to do instead. I'm just going to delete this part. So that we have a better idea of, hey, here's what this parabola looks like. And if we look from 2 to 6, you're getting exactly, you're not just getting half the area. And whatever. I wanted to show you that, but that's not really what I want to do. So I know there's a way to do. Oh, sorry, there's a way to do what I wanted, but I don't remember what it is. Anyway, if we look at this here, you can kind of see that there's exactly symmetry. So that if you drew a line down the middle, down the axis of symmetry, as it was actually called for a parabola, you would get exactly half the area on the left of 6, half the area on the right of 6, and it would be balanced, right? It's a symmetrical shape, so it wouldn't tilt either way if you were trying to balance it on that point. And so what that kind of shows us graphically is that we actually do have the mean there. Also, if you calculate in this shape where you have symmetry like this, the median and the mean would be the same. So if we calculate the median, which we're not going to do because we're out of time, you would find the median would be 6. And then I don't know what the variance would be. Maybe so here's what I'll say. I'm going to do this problem too, and I will find the other things, the variance, and I will show you that the median is also 6. I'll do a video of that as well. But we are out of time. So if you have other questions, don't hesitate to write them on the discussion or send me an email. And I will definitely do the videos that I said I would do. Probably, I'll probably do them after 2:30 today because I have office. Oh yeah, I have office hours from 1:30 to 2:30. So if you want to come see me during office hours, you're certainly welcome to. And I think that's all I got. All right, make sure you fill out the attendance, and I'll talk to you all later. You're all very welcome, as usual. Good seeing you all.